I'm going to start this YouTube series by asking you a question, and it's not a question about math per se, it's a question about stories. But more specifically, if you strip down any story down to its fundamental elements, down to its skeletal structure, what are we left with? Now, we want to think as abstractly as possible. We don't want to have any specific features included in this skeletal structure. As a consequence, that means that this structure needs to have the quality such that no matter what arbitrary book I pick from my bookcase, I could map the book's story to the skeletal structure. Sort of like how horoscopes are so vague that they can apply to anyone at any point in their lives. At the same time, we don't want our definition to be so vague that literally anything fits in it. My idea is that we'll probably need a main actor or actors, and remember that this is abstract. Our actor could be anything, from a human to a coral reef. Also, something needs to occur that requires our actor to act. Whatever happens, we'll call it the problem, and just as our actor was abstracted, our problem is also abstracted. It could be anything. Whatever happens during this narrative, we'll say that it happens on the story arc, where various influences may change and shape our main actors. Eventually, the tension from these influences and from the problem itself will spark the climax of the narrative. And then for good measure, make sure that we include dialogue, a family lesson, an explosion, and a heteronormative romance at the end. Okay, so maybe I got a little specific at parts, but we got the main idea for the flow of this narrative. And what we've just done is called abstraction, and it's something we do a lot in real life when we're looking for something vague and not specific. But before we wrap this example up, let me ask you a follow-up question. It'll be short, I swear. So if you're hearing a story from a friend, or watching a movie, or reading a book, or whatever, what are always used to tell the story, but are not fundamental to stories themselves? Now bear with me as I get a little philosophical and very #deep. What we don't need are words. If you don't believe me, look at our skeletal structure. Words isn't on it. Well, words are on it, but you got what I'm saying. But maybe an example will help make sense of this. So, when my twin from Lithuania comes into town, and he only speaks Lithuanian, it's not uncommon that we try to have a conversation about the movie Titanic. And while we both may know the story, and we're both astute proclaimers of Leonardo DiCaprio's boyish charm, we couldn't talk about it because of the language barrier. But we both know the movie, so what gives? Well, the point of this fleeting analogy is that there's a big difference between the ideas of a story, and then the tools we use to communicate the story. Let me give you an abstracted example. So, let two people exist, where the first person has an idea and he wants to share it with the second. Disappointingly, it seems that we live in the Middle Ages because we can't just upload our ideas onto the Wi-Fi and send them. In lieu of that, we need to use the medium between us to get this idea across. And since the medium is air, I presume, the first person will use his voice and his words, with hope that the second person will receive this information and then form the same idea in his brain. So we've made this important distinction here. The information that crosses the medium, even in its aggregate, is not the idea itself. And from this perspective, ideas can only exist within a mind. That means stories, too. What's funny, though, is that the first and second person from this example probably have very different ideas in their heads due to errors just in the communication. And anyone who's had a bad teacher knows this. Your teacher may be really smart, but completely unable to encode his knowledge into words that students can digest. So, just like how a bad teacher's babble isn't knowledge, a movie isn't just moving pictures, and a story isn't just a group of words on a page, so too is a group of mathematical symbols, not math. Wow, the introduction is actually over. My name is Jacob, and I'm your long-winded math student from the US. And I swear I'm not soliciting you when I say that math can be intuitive and actually a little interesting. For transparency, let me concede my reasons for why I'm here and making this YouTube series. Number 1. This past year at college, I've been a teaching assistant for a math class, and I fell in love. Oh, not with a student, with teaching math. I think that'd be against the rules. Number 2, I just want math to be accessible and interesting to everyone like it is for me. Number 3, I love attention, and I heard that the internet is full of opportunities for it. And number 4, to challenge myself, my ability to teach, and my true understanding of math and logic. Isn't that a handsome reason? So the topic of this video will be notation, and in rhythm with the introduction, I won't speak too much about particular mathematics. Please don't be delighted by this, because you're already really hurting my feelings. I'm doing this because we need something a little more fundamental before we talk about math. We need to agree on what it is and how we express it. So definitively, and maybe a little repetitively, I ask, how do we express ideas? And that answer, at least for this series, is notation. Now this is a vocab word, people, so take out your notes and listen up. I'm defining notation to be the method of expressing ideas through specific objects and form. Objects are the sounds and symbols that we use, and bundled within each object is its use and its meaning. Form, on the other hand, includes the rules of when certain objects or groups of objects or syntax should be used. Now this definition is intentionally vague, partly because I made it up and also because it's supposed to be an umbrella term for any sort of communication. But before we jump into the notation of math, let's take a look at English, which I assume you speak, because it'd be awfully weird if you didn't right now. So the English notation's objects consists not only of our words, but also the sounds attributed to them. The English notation's form specifies syntactical rules, the definition of a complete sentence, and all that we learned in grammar class. While learning specific grammar rules at times may seem silly or just downright arbitrary, it's actually kind of important. For instance, what happens when two people differ on a definition of a word, but try to communicate? If it causes an argument, we probably call that a miscommunication. If two people share no definitions, then they probably don't speak the same language. So by defining generally agreed upon form and definition, we reduce confusion by having everyone adhere to the common standard, even if that standard is arbitrary. In fact, most of them are arbitrary, like the weight of a kilogram. It's completely arbitrary. God himself did not descend from the heavens to deliver unto the International Bureau of Weights and Measures a holy platinum bar, consecrated to forever be the defining kilogram. In reality, we just force everyone to adhere to a platinum bar we picked. So now, with a mutually understood notation already in set, we share our feelings and thoughts by converting them into English, having the other person hear our words, and then having the other party decode them. But here's when it gets a little weird. Believe me when I say that math is nearly identical to English when we abstract away the nouns and polynomials and inverse functions and compound statements that differentiate our notations, just like how we abstracted the modern story in the beginning of this video. Broken down to its core, when we've abstracted all detail from math notation and English notation, we're left with our common ancestor, the idea of notation itself. And remember that notation is no more than what we defined it to be. Notation, the method of expressing ideas. That's all math and English really are. They both follow the process of encoding, transporting, and decoding an idea, so let's get our toes just a little wet with a little math notation. It'll be fun, I promise. Alright, so thousands of years ago, when the first proofs for the Pythagorean theorem started to arise, the method of sharing this formula with others proved difficult. You probably know the Pythagorean theorem, a squared plus b squared equals c squared, with some caveats about a triangle. But in Pythagoras' age, there was literally no math notation. But the Greek language existed, so we used that instead. The sums of the areas of two squares formed on the two lesser sides of a right triangle is equal to the area of the square formed by the other side of the triangle. But if you're like me, you're probably thinking, that's rather wordy, and I'm all for cutting corners. So what's the difference between this definition and the one we know? Advantages for the Greek way. 1. Anyone who knows Greek will understand what he's saying, given that they understand the math words he's using. And honestly, that's all the advantages I can think, so I'm going to move on to the advantages of the modern way. 1. It's short and it's concise. 2. It's not ambiguous because we're not using English words which can have multiple meanings. And 3. It doesn't require knowledge of Greek or any real historical language for that matter. I can hear you asking your computer screen now, Jacob, which notation should I use? Well, the true answer is, the way you choose to notate your quantitative relationships is completely up to you, man. I'm just some guy on YouTube. In fact, I won't even tell you that a particular notation is in the absolute correct or incorrect. When looking for a notation, you probably want a convenient one though, so here are some traits you should look out for. Alright, so first of all, the notation should be time and energy effective. Say I taught an English class and forced you to turn in all of your essays in the form of videos where you present the essay in American Sign Language. You would probably have some interesting signs to show me. Number 2, the notation should minimize ambiguity. We want to overload a symbol as few times as possible. And when I say overload, I mean using the same object for different functions. Given the right context, it's okay to overload some objects. For instance, the phonetic object of the word write is overloaded. But when I said right context, you knew I meant with an R and not with a W. And 3, we want the notation to be legible and teachable to others. Remember, we use notation to keep track of ideas, and if we can't share it with other people, we're losing a lot of what we want. Just like how you need to pick the right tool for the right job, you need to use the right notation for the subject. This tool metaphor continues though, because notation really is a tool. And just how there isn't a right hammer or a correct hammer, hammer. There's just a good or a bad hammer. And notation, just like hammers, are made up. They're inventions by humans. What's interesting is when we try to look at the history of the notation that we use today. We didn't always use it, as the Greeks know. Modern notation is a melting pot of the most useful and efficient of those symbols. It's a survival of the fittest of the best notation. If there's a poor notation, people are going to try to invent a better one. It's the same reason we don't use triangle-shaped wheels on our cars anymore. If we ever did. Because it'd be terribly inefficient. So if someone asks you, why do we write equations the way we do? It's so confusing. You should humbly reply, well, how would you recommend we make it better, smartass? But I digress. I hope that this opens your eyes, at least a little, to the significance of notation in all forms of upper-level thinking. Notation is so fundamental to us as humans that we even think in the notation of our mother language. Cognitive scientists like Noam Chomsky have claimed that what makes the human brain so powerful is our ability to just name things and put things into words. We're not like dogs whose intellectual capacity halts at imagining pictures in our heads to substitute a line of thought they can't articulate. This is a popular idea. In George Orwell's 1984, one method of brainwash by the totalitarian government was to remove words like rebel and espionage from the language, as it was thought that the removal of those words would discourage the formation of those ideas in their heads. By harnessing notation, we can abstract and keep palpable the concepts which, while they may seem fleeting in our minds, will remain permanently saved when written on the wall of a cave, or a notebook, or a YouTube video. But as Pythagoras and a plethora of other mathematicians and logicians have throughout history realized, it's not easy to perform quantitative analysis and solve logic-based problems when we're forced to use a notation developed to warn an enemy tribe is attacking or to encapsulate the joy and sorrow of Shakespeare. To graph the population of penguins throughout time, to find what velocity and angle to fly a plane, or to predict the weather in the stock market, we need something stronger than English. What we need is a concept to be discovered and a notation to be invented. And that's math, baby. Thanks so much for watching, guys. In the next video, I'll talk about modern mathematical notation from the ground up and how we use it to solve real-world problems. You'll witness the birth of the equal sign and the spooky, mysterious axioms. Have a great day.